The space between stars is not empty, but contains traces of gas and dust, the interstellar medium from which stars are born. As stars age and die, they return material to the interstellar medium, enriching it with new elements, sometimes in cataclysmic supernova explosions that can be seen across the galaxy. There is a cosmic cycle in which material goes from the interstellar medium to the stars, and then from the stars back again. Some of the cycle is easily seen. Star clusters recently formed from interstellar matter. Stars in their middle years. Stars at the end of their lives. Whilst spectacular supernova explosions blaze forth the death of some massive stars, most stars end their lives less violently, shedding shells of material called planetary nebulas, giant smoke rings in the sky. The material from the stars replenishes the interstellar medium and helps to form the great clouds of gas and dust where the new generation of stars is born. It is this part of the cosmic cycle, starbirth, that is shrouded in mystery behind dark curtains of dust and gas, where dense clouds of molecules concentrate under gravity to form stars. How can astronomers see what's happening through these curtains of dust? Can visual images reveal all, or do we need wavelengths outside of the visual range?
Here we have a visual image of the star formation region GDD 27. This region is located relatively close to the galactic center in the constellation of Sagittarius. The region is dominated by dense molecular clouds, although we can see some young stars in this image. It is only when we go to near-infrared wavelengths that we can probe deep within the molecular cloud and actually see the young stars that are being formed.
So it is not the familiar visible wavelengths that probe stellar birth, but wavelengths that are invisible to our eyes, the near-infrared.
This is a near-infrared image of the same region we just saw in the visual, and we see a totally different picture. In the center of the field, we see a very bright infrared source and very extended diffuse emission going to both north and south. This emission is part of the bipolar outflow of the source and is material leaving the source and re-entering the interstellar medium and molecular cloud. We have now color-coded the emission from this source so that red is the brightest emission and blue is the faintest. This color code allows us to study in more detail the diffuse emission and gives better contrast between the fainter and brighter parts of the image.
Infrared radiation from behind a curtain of dust reveals a star forming from a fragment of the interstellar cloud contracting under gravity. Much of the flow is inwards towards the star, but the infrared image reveals that some of it is immediately ejected to create the bipolar outflow.
We are now going to look at the emission in several regions of GDD 27 to study the physical processes taking place at these locations. The first position is located directly in the center of the source, which is called IRS2. The second position is 10 arcseconds south of this, and the third position is 20 arcseconds south of IRS2. This is a spectrum of the central source. It shows a rising continuum level from short wavelength to long wavelength in the near-infrared, and this is typical of thermal emission from hot dust. This spectrum is of a region 10 arcseconds south and shows a rising red continuum again, but superimposed on this are emission lines from molecular hydrogen. These lines are formed when outflowing gas from the central star hits interstellar medium molecules and excites them. This is a third spectrum of a region in GDD 27, which is located 20 arcseconds south of the bright central source. The gas in this region has been totally ionized by the hot ultraviolet flux from the star, and as it reforms, it forms this line.
What all these data show is that here is a region where stars are forming. This bipolar outflow is created by a young star embedded in IRS-2 or nearby, a star in the very act of formation. The first spectrum from IRS-2 is thermal emission from dust, heated to about 1200 degrees Celsius by the young star embedded in it. The second spectrum not only reveals hot dust, but also spectral lines from hydrogen molecules that are excited by the gas flowing from an embedded young star or its ultraviolet radiation. The third spectrum has spectral lines that show the region is ionized, and this is thought to be the result of strong ultraviolet radiation from the nearby star IRS-1, a star that is very nearly fully formed. How do astronomers obtain these infrared images and spectra? They must climb up here to the highest point in the Pacific Ocean, close to the summit of Mauna Kea on the Big Island of Hawaii. At 14,000 feet, there is so little water vapor left in the atmosphere above that the infrared radiation can reach the detectors in these domes. This makes it a particularly good site for UKIRT, the United Kingdom Infrared Telescope.
The problem with observing in the infrared is that the atmosphere itself, although transparent, also glows. It shines in infrared radiation. The telescope also glows in infrared radiation, so we have to design it in such a way that the instruments on the back of the telescope see as little of that background glow as possible, which would otherwise smother out the radiation from the cosmic sources that we're intending to observe. The secondary mirror moves to and fro through a small angle so that we can alternately see the source and background together, and then the background by itself. This helps us to identify the infrared radiation from the source from the much larger quantity of background radiation. But how do we detect infrared radiation?
Recently, there have been some big improvements in how we make infrared detectors. Not so very long ago, infrared astronomers had to use just a single, very, very tiny detector to look at just a tiny patch of sky. So if we wanted to make a picture of the sky at infrared wavelengths, then we had to measure each little point, 1 point at a time. But now we have two-dimensional arrays of detectors, and these are still very small and not much to look at in somebody's hand, but when we look at them up close under a microscope, you can see that it is made up of rows and columns of individual detectors, and we call each one of these a pixel. Round the outside, the tiny wires read out the signal from the detectors. This is ERCAM, which uses one of these infrared chips to make pictures, and to make a picture, the light comes in through these two mirrors and is focused inside the camera, where it is kept very, very cold by the closed cycle cooler, which works a little bit like a refrigerator. And by doing this, we can make pictures of the sky thousands of times faster than we could before. And this is an example of a picture made by ERCAM. And what you can see are the little red dots, which are stars, and also a big fuzzy region, which is the interstellar medium, where it's being heated up by the young stars which are forming here. Now, another instrument on this telescope, a spectrometer called CGS-4, uses one of these chips in a different sort of way. With an infrared spectrograph like this, we use the chip to image a small strip of the sky along a column of pixels. Then for each pixel in the column, we use the spectrograph to spread the light into a spectrum along the row. Here is an example of some CGS4 data. You can see some bright vertical stripes on the image. This is a spectrum of the sky. And then superimposed on this, you can see a bright horizontal line along row 25, which is a spectrum of a star which is much brighter than the sky. Underneath the image, we've made a graph which shows how the brightness of the star changes with wavelength. And this is what we mean by a spectrum. Infrared spectrographs like this are a really exciting development, because by splitting the light up into its spectrum, we can study the chemical composition of the interstellar medium, or look at motions within the interstellar gas.
Therefore, with images from cameras like IRCAM and spectra from spectrometers like CGS4, astronomers can study the events leading to star formation and the birth process itself. Our sun must also have been through similar birth pangs, for it seems to be a typical star. All the material, molecules and dust that went into its creation has been torn apart. But perhaps leftover fragments of dust still survive today, somewhere within the solar system, in more or less pristine condition. Where should we look? Here in Antarctica, amidst all this snow and ice, rocks are easily seen. But these scientists are not interested in ordinary Earth rocks. They're looking for meteorites, rocks that have come from space, rare fragments from the Moon and even from Mars, but mostly from the asteroid belt. Within some of these, there may be dust left over from before the sun was born.
Nice little guy. Yeah.
This dull-looking rock is the sort of thing that we're prepared to go to the ends of the Earth to find. It's an unequilibrated ordinary chondrite. On most sides it's rounded, but where we've cut a face, you can see quite clearly the rounded, light-coloured inclusions, which are the chondrules, which give the meteorite its name. It's unequilibrated because since it was formed 4.5 billion years ago, it's never been heated hot enough for the components to mix together.
But what is the evidence that such meteorites do indeed come from outer space? Scientists study their chemical elements. An element is made from atoms containing a particular number of protons in the nucleus. But the number of neutrons can vary, each unique combination called an isotope. In this case, carbon-12 is the most abundant stable isotope, but carbon-13 also exists. So the carbon in any substance will be a mixture of isotopes in certain proportions, the isotopic composition. Like a genetic code, it tells us about the meteorite's origin.
About 20 years ago, people began to study meteorites like this by heating them up to release the gases which were trapped within them. They found that as they increased the temperature, the isotopic composition of these gases changed to give values which were quite unusual, things that had never been seen before. And these values became known as isotopic anomalies. Clearly, researchers were interested in finding out what isotopic anomalies were, where they were located in the meteorite, and what caused them. And so experiments were devised to look at the various components, to dig pieces out and analyze them separately. But this didn't actually give the answers to the questions that we had. The reason being that the anomalies were associated with the matrix, which is a small part of the meteorite, which actually acts like glue to bind the larger grains together. You can see a sample of matrix around this chondrule here. It's a dark, opaque, almost black-like substance. This can be seen much more clearly, of course, by cutting a section from the rock, polishing it and looking through with a microscope. To get at the material in the matrix, rather surprisingly, the best thing to do is to destroy it. And this can be accomplished by using different acids to dissolve away the minerals which are present. As soon as experiments like this were started, it became quite apparent that 99% of the meteorite could be destroyed, and yet the material that carried the anomaly remained intact. And so the isotopic anomaly became much more apparent as isotopically normal material was used. After a while, the only thing that remained in the residue was carbon. A way of investigating this was to burn it gradually, increasing the temperature. To our delight, 99% of the carbon burned with an isotopically normal composition at 500 degrees. But at much higher temperatures, 1% of the carbon had an isotopic composition which was bizarre. The only place it had ever been seen before was around highly evolved stars where nucleosynthetic processes converted carbon-12 to carbon-13. What had been discovered is that meteorites like this contain interstellar grains which lived before our solar system was born. Not surprisingly, this experiment is often being referred to as burning down a haystack to find the needle.
The McDonnell Center for the Space Sciences at Washington University in St. Louis is one of the world's great centers for investigating meteorites and moon rocks. Here they are analyzing individual dust grains that formed around stars, which were old before the sun was born. Under a powerful scanning electron microscope, the tiny grains, extracted from the matrix of the meteorite, look like this. Roughly spherical and crystalline, they often show signs of gas bubbles from cavities that may have formed during the chemical isolation process. This is an interstellar graphite spherule just 4 micrometers across. In this remarkable section view, we can see how it seems to have gradually built up in layers or scales around a central carbon core. And during this process, it has gently entrapped a tiny fragment of material from a long-dead star. We're looking at a microscopic crystal of titanium carbide, which for billions of years has remained cocooned, retaining the chemical fingerprint of its origins. It is the carbon in grains like this one, or silicon carbide, that give rise to the carbon isotopic anomalies. In this laboratory, they're using a state-of-the-art machine to investigate the isotopic and elemental compositions of individual particles from distant stars.
What we are doing here in this laboratory is to specialize in the isotopic analysis of individual grains, which are only a few micrometers in size, in an instrument called an ion microprobe, which essentially is a mass spectrometer. The ions for the mass spectrometer are generated by bombardment with other ions. In our case here, we bombard the sample surface, the grains, with cesium ions. These cesium ions knock out individual atoms out of the grains in a process called sputtering. In this sputtering, you generate ions and send those ions through the mass spectrometer. The mass spectrometer selects different elements, but also different isotopes of one given element. What we see in this instrument actually is an image of the sample surface, and in this case of individual silicon carbide grains in mass-selected secondary ions. So that means we can get images of carbon-12 ions, we get images of carbon-13 ions, and we can compare these images in this way, measure the isotopic composition of these grains. How do we know that these grains are interstellar? Well, we know it from the isotopic compositions. The isotope of elements like carbon or nitrogen are made all in other stars, and they're made in different proportions. So if a grain was formed in the atmospheres of one of these stars, it should actually have a quite different composition from solar system material, because solar system material is a mixture of all this material coming from different stars. What is shown here are the isotopic ratios of nitrogen and carbon measured in individual silicon carbide grains. The two lines in the center of the graph are the isotopic composition of solar system material. That means where the two lines cross, that would be the nitrogen and carbon isotopic composition of solar system material. As you can see, the silicon carbide data points deviate largely from this isotopic composition. They're mostly in the left upper corner, which means that the grains are enriched in carbon-13 and enriched in nitrogen-14. It turns out that we actually have information on the isotopic composition of stars, and isotopic compositions like these are observed in a certain type of stars called carbon stars. These are stars where the nucleosynthesis of carbon, nitrogen, and oxygen is influenced by hydrogen burning. We don't know where all of these grains come from, but we know one thing: they come from other stars.
The interstellar medium is constantly being changed by vast outpourings of matter from dying stars, which eventually may be incorporated in future generations of stars. So perhaps it isn't surprising to find the occasional grain from another star which we can identify, because it has a different isotopic composition from the average mix of elements that make up our solar system, including the Sun itself. In about 5,000 million years, our Sun will enter old age. It will swell to become a red giant, in the process engulfing the inner planets, meteorites, and the Earth itself. Much of its mass will be blown off into space to replenish the interstellar medium with gas and dust, as part of another turn of this great cosmic cycle from which we've come. Will there always be new suns, new stars? Well, there will be as long as there is hydrogen to act as nuclear fuel inside them. This fuel sustains the stars throughout their lifetimes. But gradually, the nuclear processes inside them are converting more and more hydrogen into heavier elements. Hydrogen nuclear fuel is becoming scarcer in the interstellar medium. There will come a time in the far distant future when stars can no longer burst into life, and the cosmic cycle will slowly dwindle to nothing. The lights will go out all over the sky.
Campaign